These are the textbooks. So the first textbook for this course is IC Engine Fundamentals by J.V. Haywood. This is the best book available in IC Engines. Almost we call it Gita of IC Engines. And then the second book is Fundamentals of Internal Combustion Engine, Gill, Smith and Dury. For those of you who have not done first level course, I will strongly recommend that within 3 days you read this book. This is like a novel, very, very fundamental book written in 1950 by 3 gentlemen in US Navy. And this is very fundamental just to understand what IC engines is. And if you read this, then I think this course will be easier for you to follow. Third book is Internal Combustion Engine in Theory and Practice by C.F. Taylor. Fourth book is by IC Engines and Air Pollution by Hobart. And then the last book is Hydrogen Fuel for Surface Transportation by Joseph Norbert. In addition to this, I am also prescribing few SAE publications, okay, which you can look at, and these SAE publications will be helpful in looking at specific topics, okay, and these are mostly available in our library. So coming to the course, this course is on alternative fuels and advances in ICC. So as I was mentioning to you, it is necessary that you have the first level knowledge of the IC engines, and therefore I highly recommend that if you have not done ME 359 or at least one course in undergraduate in IC engines, you should look at the book of Gill, Smith and Dury. It's a very good book, you can read it in 2 or 3 days. This is a more advanced course, so I will be only covering the advanced topics. In this course, we will be starting with combustion and fuel. We will be looking at combustion processes in SI 3 engines. You can note down. And we will also look at petroleum-based liquid fuel and the refining process. Okay. And then we will be looking at alternate liquid fuels. Alternate fuels which are liquid, for example, vegetable oils, biodiesels, alcohols such as ethanol and methanol, emulsified fuels. We will also be looking at lubricating oil compositions, and if you change to alternative fuels, what will be their effect on the lubricating oil? Because that's also very, very important feature if you want to switch over to another fuel. We will then be looking at gaseous alternative fuels. So what are the gaseous alternative fuels of importance? The first is hydrogen, which is called freedom fuel. Okay. Then we will be looking at compressed natural gas, liquefied petroleum gas, dimethyl ether, and something called ethane. Ethane is mixture of hydrogen and methane. I comes from hydrogen and thane comes from methane. So we will be looking at some of these fuels in this course, and then we will be looking at some of the modern developments in IC engines which have taken place in the last 20-25 years. Okay, so for example, we will be looking at technologies such as EGR. EGR stands for exhaust gas recirculation. Okay, we will also be looking at multi-point port fuel injection, MPFI. We will also be looking at one very relevant technology which has not come in India yet, but it's a very important technology. It's called gasoline direct injection. We will also be looking at futuristic technology which has not come, which is not commercial anywhere in the world right now. It will come in future. This is HCCI, homogeneous charge compression ignition. Okay, and then we will be looking at turbocharging. So some of these things we will be looking at great detail. And beyond that, we will be looking at optical measurement of techniques and tools, because these optical measurement techniques have actually revolutionized the way we understand combustion and the way we develop the IC engines. So far, until last 15-20 years, what is happening inside the engine combustion chamber was a matter of speculation, because it's a metal engine. You're putting in fuel, the combustion is happening in 10-15 milliseconds, the entire engine cycle is over. Processes are really very fast, and you can only speculate what is happening. You can only guess. You are not sure of the things that you think are happening. Okay, but things have changed in the last 15-20 years. People have developed optical engines. So now the top part of the engine is made of glass. So you can actually put in light. Modern cameras are very, very high speed, so you can really take high speed imaging. Okay, and then you can play the video slowly, so to understand the process in slow motion. Okay. So process which is happening in 20 milliseconds, you can expand it to 20 minutes and understand frame by frame, what's going on. So this has changed the entire understanding of the IC engine combustion processes. Many different new techniques have been developed in this area. Okay. So we will be discussing particle imaging velocimetry, which is nothing but flow visualization technique. So inside the engine, how the flow is happening, because flow is going to affect fuel air mixing inside the combustion chamber, and fuel air mixing is going to determine how the combustion happens, how the pollutants form, and how the emissions come out of the engine, how much power is generated, how much torque is generated. So fuel air mixing is the fundamental process, and for that PIV will be used. Okay. So one is two-dimensional PIV, that means you are looking at velocity vectors in 2 dimensions. If you look at 3 dimensions, it becomes 3D, and the way you represent, you must have seen holograms which are actually 2D, but they give impression of 3D. They give you the impression of that. So that's called holographic PIV. So we'll be looking at some of these things. And also we'll be looking at spray visualization. Because in the engine, there are two most important fundamental processes. One is fuel spray, the other one is fuel mixing. Okay? These are the absolute fundamental processes which are governing combustion and emission formation. So we'll be also looking at spray visualization, spray characterization. In addition to that, we will be looking at phase Doppler interferometry. Phase Doppler interferometry is a technique which is used to measure the droplet size of the spray that is coming out in the combustion chamber. Okay. So now you see, when the spray of few milligrams of fuel is done and very high pressure in a diesel engine. How high pressure? It could be anywhere between 200 bar to 2000 bars. Okay. Very high pressure. So when you are injecting such a small quantity, what you are essentially doing is you are creating millions of very, very small droplets. Now when I say very small, how small I am talking about? Any guesses? So this will be roughly from sub-micron to few microns, tens of microns. Now larger is the droplet, more difficult will be mixing with the air. Smaller the droplet, will mix more quickly. So therefore it is very important for us to understand what is the size distribution of the spray. So this size distribution is actually done by phase Doppler interferometry. So this is one of the cutting edge technology which has been developed for spray characterization, and I will tell you some of the special feats that we have achieved in IIT Kanpur as far as this technique implementation is concerned. So far people are able to implement this only in the spray chamber. Okay, you have chamber, you are injecting and you measure. But for the first time in the world, we have been able to successfully measure inside a firing engine. So now engine is moving, real-time processes are extremely fast, as I said, we were able to successfully measure the pressure distribution. So we will be discussing some of this. Then I will also be talking to you about optical engines. Okay. This is one tool, as I mentioned, in the last 15-20 years they have been developed, and they have given a lot of power for engine developers. So, and then I will be talking about engine endoscopy. So endoscopy, are you familiar with endoscopy? Endoscopy is a technique which is traditionally used in surgeries, in medical science, where you don't have to really cut yourself open, just make a small hole, put a camera inside, and do the surgery and take out, and within like few hours or few days you're able to work it out. Okay. So basically a small hole to see inside in great detail. So that's what we do in the engines also. Okay. So when you make optical engine, the entire liner is made of glass. So mechanical structure in a way is weak because glass is not as strong as metal. So you cannot really run the engine at very high speed and very high load. That's one of the limitations of optical. Suppose you want to understand the phenomena at high speeds and high loads, where the firing pressures are very, very high. So what do you do? So we employ this technique. What we do is we make a small hole. So just a small hole, so structure is not that weak. Put the endoscope, protect it from the combustion gases, and take the pictures inside. So we exactly know at high speed, high load, how things are happening. If you want fundamental understanding, we go for optical engines. If we want high speed, high load visualization, we go for engine endoscope. So we'll be discussing some of these things. We will also be discussing about many pollution measurement instruments and techniques that are used. For example, suppose you want to measure NOx emission, how much NOx is coming out, how much carbon monoxide, carbon dioxide, particulate matter, okay, how much hydrocarbons. So all these species, how much of them are being produced in the different locations. So we will be discussing the instruments and the techniques used to measure these pollutants from the engine. Then the next part will be that once these pollutants are formed, how we are going to control them. So there are many different techniques which are used to control the pollutants that are coming out. These techniques are as simple as catalytic converters. Most of the gasoline engines are catalytic converters, which were implemented in 1990 in this country, 1992 to be precise. Okay, but after that, many other new techniques have been implemented in our country, and also some of them are yet to come. DOC has already been implemented. DOC is diesel oxidation catalyst. Okay. DPF is diesel particulate filter, which is making its way into India. SCR is selective catalytic reduction, and lean NOx trap. So these two are basically for particulate control, and these two are basically for NOx control. So far in India, this is the only one that has been adopted. These two are really on the way, and once we are going to implement Euro 6 emission norms in April of 2000, it will be necessary for us to have these techniques. So therefore, industry is really looking forward to implement this, and right now, this is what is the requirement of the industry. People who know about these techniques are really required in the industry. To the next topic. So today I am just introducing you to the overall scenario of energy and where the transport sector fits in, and why should we do all this work here. So this is a very famous curve which has energy intensity on the y-axis and per capita income on the x-axis. Okay. So what it is showing is that there is almost all, these are different countries which are there on this line. What it is showing is that as you tend to earn more per person in the economy, you tend to consume more and more amount of energy. Of course, when you become wealthy, you would like to have a car. If you are more wealthy, you would like to have a bigger car which gives you lesser mileage. Okay, so your energy intensity keep on increasing. That's what is seen here. So if you look at most of the country, at the top of the line, you have America. Okay, then you have Australia. America is on this side. What does it mean? If you are on this side of the 45-degree line, it means you are actually spending more amount of energy than the global average. Okay, so this is called energy spendthrifts. You are wasting a lot of energy. Okay, then this is Australia. Then here we have Japan. If you are on this side, that means you are really you consider the pollution that you are generating, and you are conscious that you should not be consuming so much energy. So you are more economical in terms of energy. Here is Mexico, here is Brazil, this is China here, and this what you see in this green color. Okay, here they are. You can't even see it. Okay, so this is where we are. Now imagine Indian economy is growing, right? It's growing leaps and bounds at rate of 8 to 10%, and it's expected to grow even more. So we'll move on this axis. If we move on this axis, obviously we'll move on this axis as well. So it's going to be a huge challenge for us to follow this trajectory. If we follow this trajectory, right now at this income levels, we import more than 80% of our petroleum by spending close to $700 billion per year. Suppose in next 3 years or 4 years we double our economy size. Can we afford to import $1,500 billion? Answer is no. So then we have to look for some kind of a flattening of this curve. That means we have to make our people realize that they should be economical as far as energy is concerned. We can't afford to go for same curve. Okay? And in fact, India has shown the way in this direction. I was just talking to somebody yesterday, and he was telling me that 10 years back we used to generate close to 70 to 80,000 megawatts power. And today our economy has grown several times since then, but our energy demand, energy demand has risen to 130,000 gigawatts, which is less than double. Okay, so that means that Indians are becoming more and more conscious, and more energy efficiency is coming in all sectors of the economy, which is good. Okay. So the challenge that we are facing is, right now the global population is 7 billion. In 2050 this will be 8 to 10 billion, about 1.5 times, which is only 30 years old. 80% of, right now 50% of people are living in urban areas and 50% in rural areas. In 2050 it is expected that 80% people will be living in urban areas. So that means what? Rural people tend to spend less amount of energy. Urban area people tend to spend more amount of energy. So here this will go on. Then the average incomes will also rise globally, because overall the world economy will obviously make more progress, and the average income levels will be $15,000 to $25,000 per person on a global level. Okay, so this is going to go up. So obviously the energy demand on this point of view also will go up. So that means by 2050 you will require at least 2 to 3 times more energy compared to what you have today. And we are only 30 years away, 35 years away from 2050. Okay. So we are facing an immense amount of challenge. How can you meet those challenges? First is that meeting those challenges by conventional sources, fossil sources, is extremely difficult. Not only extremely difficult, it is also environmentally unsustainable. Whatever fossil fuels you have, what are the fossil fuels? You have coal, you have petroleum, you have gas. These are the 3 main fossil fuels. So they are below the earth crust. You take them out, you use them. You use them, you produce carbon dioxide. Where do you put them? Into the atmosphere. As a result, what you are essentially doing is you are pumping the carbon from below the earth crust into the environment. CO2 concentration therefore is going up. And what that CO2 concentration does? Global warming. Okay. Just to give you an example, the carbon dioxide levels in the earth crust were 280 ppm in 1850. Why 1850 is so important? Because the industrial revolution took place in 1850. And industrial revolution means we started using coal at a large scale in our industrial processes. And since then, we started putting carbon dioxide into the atmosphere, and as a result, now today we have 406 ppm carbon dioxide, and this carbon dioxide is not constant. It's a function of time. Because with time we put more amount of fossil fuel into the atmosphere. So how can we, when we have to arrange for such a vast variety of vast amount of fuel for our next 30-35 year time frame, how do you go about it? So the option that we have to actually encourage using non-CO2 or CO2-free renewable energy sources. What are those? So I'm not just talking about transport sector, I'm talking about overall energy sector. So you could use more hydro. Okay, hydro is completely CO2-free. You can use geothermal, that's also CO2-free. Geothermal means the heat inside the earth crust. You have solar photovoltaic, absolutely CO2-free. Solar thermal, wind energy, hydrogen energy, biomass or biogas. This is also CO2-free because biomass, when it grows, it absorbs carbon dioxide from the atmosphere, use it to generate heat or energy, and then you put the same CO2 back. Next cycle of the problem, the same CO2 again captured, so it's also CO2-free. Different types of alcohols. Biodiesel is also biofuel origin. And then I have also looked at renewable energy sources, CNG, LPG, in the sense that if you have biogas, you can actually convert it to natural gas and then natural gas. Okay. So from that perspective, it is renewable. If you are taking it out from the earth crust, it is non-renewable. Okay. So these are some of the renewable energy sources, and non-renewable energy sources are, even the nuclear is non-renewable. Once the fuel is spent, it is spent. Natural gas, fossil fuel, coal, these are all non-renewable fossil energy sources. What are the implications if we keep on using these these fossil fuels? First is that it leads to reduction in underground based carbon emissions. Essentially, you are removing the carbon, so the stock below the earth will actually reduce. It leads to serious modifications in Earth's surface layer, atmosphere. Why? You put CO2, you put oxides of nitrogen, you put oxides of sulfur, you put carbon monoxide, all kinds of gases. Then most of these fuels you are actually extracting through process of mining. Now when you do mining, not everything is really what you are looking for. There is a lot of undesirable things also come out. So what you do, you put them in one side. So that also occupies a lot of space, and a lot of surface ground undergoes subsidence when you want to go for coal mining. Okay, so if you go to any of these coal mining areas, coal mines will be in a very small area. There will be a lot of space where there will be dump, waste dump, which is coming out of mines. And this is increasing the CO2 levels in the atmosphere. I think this is the old data. This is 406 now. 350 we used to have in 1980s. CO2 levels are still climbing as a function of the fuel that we are burning, which is leading to greenhouse effect and acid rains. Acid rains is because of sulfur, because coal has sulfur, sulfur gets converted to sulfur dioxide, atmospheric moisture gets in contact with it, and it forms sulfuric acid and sulfurous acid. Okay, and then the other acid that comes down with the buildings, and it has not so good effect on human health. Okay, and it leads to smoke. Smoke is what? Smoke is smoke plus fog. So foggy situation when you have smoke also, that's called smoke. Okay, this smoke can come in summertime, it can also come in winter time. Winter time Kanpur we feel a lot of pinch of winter smoke, but summers also sometimes the visibility goes down. Then change of climate. Winters are harsh, summers are harsh. We are experiencing this now almost everywhere in the world, including in India. Now, coming to petroleum, people say that what will be the demand and what will be the supply. Now, petroleum is traded in open markets, and there are a lot of players. Right? Now, in a marketplace, when there is low demand, what happens? The commodity price falls. When the demand is high, the commodity price goes up. There was a time when the demand was very high, the economies were doing very good, everybody was importing a lot of petroleum, crude oil from Middle East and also from South America. The prices went more than $100 per barrel. Okay, this was around 2009-10, not really far back. And today, most of the global economy is in recession. Like last year or the year before, it was great depression. Okay, so that brought down the demand, and the crude oil prices tumbled to $30-35. Today they stand at around $50. These prices are extremely volatile to keep on fluctuating. So now, if you look at this entire system of supply and demand. So this curve tells you some information. This is a 100-year scenario, and this is the global energy demand. So you can see between 1950 to 2000, global energy demand grew at a rate of 4%. After that, it is 3%. So what is being said? This blue line, the black line is oil. The demand, as I said, will keep on increasing. But the petroleum supply will saturate first, and then it will fall. And so what will happen? There will be gap between the demand and supply. And if this gap is not met, what will happen? Not just prices, it will lead to global turmoil. It will lead to wars between different countries, because many countries invade other countries in order to control the energy reserves. Right? It has happened in the past, it will happen in the future also. So it's very important that this gap is not allowed to grow. Okay. So what is expected is that once this flattens out, the difference between the demand and supply will be primarily met by gas. So this blue line is gas. But then again, gas reserves are also fossil reserves. They are not infinite. They will also peak. So this will peak. Okay. Then what? So then comes the question of unconventional energy sources. So then the unconventional energy sources have to meet this supply, this gap. Okay. So now if you look at the unconventional energy sources as of now, they are not very economical because we have not been able to develop technologies to make them compete with conventional fuels. So this will be around 2035 or 2040. So what essentially it means is it is a challenge for us scientists and engineers to develop technologies in next 15 to 20 years such that the unconventional energy sources should compete in terms of pricing with the conventional sources. And if we fail to do so, what will happen? There will be a lot of chaos in the world. Okay? Now, question comes that do we really have so much of unconventional energy sources? The answer to that question is yes, we do have. And this curve shows that all. So here, this is hydro in light blue, and you have wind energy source, solar energy source, geothermal energy source, and biomass. Only these five are compared for different countries and different continents. Okay. Now this on this axis you have gigajoule per capita. That means per person how much energy is required. So the demand range is only this much in different countries of the world, between 100 to 200 gigajoule per person per year. Okay. And the supply, for example, if you look at North America, it is 900. Former Soviet Union, it is 1200. Okay. If you look at Asia, we also have about 150. Okay. Why it is so low? Because Asia is very densely packed. You have too much population compared to area. Former Soviet Union, why it is so high? Because they have such a big land mass, but very small population to support. If you look at Europe, Europe is very small but very densely populated as well. So here also there is a little bit of a problem. South America, Africa, Middle East of course the population density is very, very low. So if you look at the global level, we really have enough energy, non-conventional energy available to sustain our civilization. But the problem is that right now we don't have technology by which we can exploit these sources in an economical fashion. So that means that those of you who must have heard that all these solar, biomass, etc., they are saturated fields, they are really not an answer, they are more fashionable to work. It is incorrect. Actually, the time is now coming when we have to develop technologies to make them economically viable, and it requires a lot of science and engineering inputs, and so there will be enough opportunities and enough job opportunities as well in these areas. Okay? Now, one of the questions that is asked is that, once this is over, what are we going to do? We have to look at humans. Humans are very intelligent, and we have really adapted to changes very, very quickly. And I'll take you back into the history, for example. Before 1800, there were hardly any energy sources, and people were developing science in the West and also in India. But there were hardly any sources of energy. So first what we did was we started using wood. We started using wind for propelling our ships. We started using water for generating some of our things. And we started using animals. Okay. And then around 1830, coal was used to develop the steam engine. That was first mechanized transport. Okay. And so coal became our main source of energy. So steam engine was very, very popular between 1830 to 1900. In India it went up to 1970, 80s. Also we had steam engines. Then around after 1850 electricity was discovered, and electrical dynamo was used, and so coal was started. Coal was used primarily for electricity generation. And then, around 1900, 1890 and 1900, petrol and diesel engines were invented. So after that, the oil became very, very important, and we shifted from electricity to oil. Most of our transport needs were met by IC engines till 1970s, and even now, for that matter, but till 1970s, IC engines were the most prominent energy source. In 1990, for electrical energy, nuclear became fashionable. Nuclear became available, so we focused on it. Nuclear energy. Then we discovered this combined cycle gas turbines, which are highly efficient gas turbine cycles. So you have gas turbines as a topping cycle and steam cycle as a bottoming cycle. So this is highly efficient. You can reach up to efficiencies up to 50%. So this is actually going on. Today we have manufacturing advantage. We can use fuel cell, we can use hydrogen and other technologies. So I think the time has come when a fundamental shift has to be made by mankind in terms of how we supply our energy. Now this, coming to India, if you look at today, 2016-17, as I said, we have roughly around 196 million metric tons of fuel demand, and more than 70%, roughly about 80% of it is imported. Our domestic sources are very, very small, and as our demand is growing, domestic contribution is actually shrinking, and that's why Indian companies are now going on acquiring oil fields in different countries like Iran and Southern America and other places. And this is obviously causing a huge burden on foreign exchange reserves. If you look at the production versus import, this is the old data, but you can still see some trend. Total requirement was 18.5 in 1971, out of which 6.8 billion metric tons was produced in India, which is roughly around 30 to 35%. Now, if you look at 2004 and 5, this reduced to, although our production went up 5 times, but our demand also went up 6 to 7 times. So the domestic production fraction actually reduced. Today it stands at around 20%. And in future, in 5 years from now, this may well be within 10%. 90% of the energy will be imported. So next time you fill the petrol, you should think that 90% of it is coming from other countries by paying foreign exchange. Okay. So, the known worldwide reserves of petroleum are about 100 billion barrels, and these are predicted to last only about 40 years, and hence the availability of petroleum is really uncertain. So therefore, you have to consider alternative fuels for substitution of gasoline and diesel. Okay, and you have to also understand that no single fuel can sustain the urban transport in foreseeable future. So you have to really go for a variety of options. Whatever is available, whatever can sustain, you have to look at it seriously. How will the world manage the energy scenario in future? So as I said, technology and human ingenuity will ensure that future energy demand will be met fairly, cleanly, and most importantly, peacefully. We don't want to fight wars for energy. And if you want to meet the energy demand in keeping these 3 broad principles in mind, these are the things that we have to promote, particularly in India. First is that we have to go for energy conservation. Very, very important. Any unit of electricity saved or the 1 kilometer distance not traveled is produced, energy produced, equivalent amount of energy produced. So we have to conserve the energy. We have to develop renewable energy sources and also biomass based energy sources. We have to look at unconventional fossil fuels. Because conventional fossil fuels are over, so we have to look at heavy oils, tar sands, shale, coal bed methane. I'll explain what are these. See, if you look at the petroleum, where is it stored? It is stored in underground cavities. Okay. So now these cavities do not have lining; these are rock beds, and there is sand. So when you drill the hole and that a pipe pass through it, you can draw only a certain fraction. You are not able to evacuate this whole thing because large amount of this fuel is actually percolated in the is sticking to the cavity walls. It is percolated deeper into the soil. You are able to only extract 1/3 of the petroleum in economic manner. What is left, 2/3, is sticking to the walls. It is heavy, it is more viscous, and you can't really take it out. So now we have to develop technologies by which you can actually take out maybe a sizable fraction of this 2/3 that is remaining inside. So that's heavy oil, and then there are some tar sands. Like for example, there is a very famous project in Canada which is called Alberta project. So what it says is that there are tar sands. That means it is not an oil reserve, but the sand has heavy, large amount of oil content. Okay. So now you have sand which is mixed with oil, and if you can separate this oil from the sand, you have hydrocarbon available to you. Now there is a process called fracking. It was very fashionable till 2010-11 when the prices were $100 plus. Okay, so there is a lot of politics behind it. The politics behind it is that the tar sands have very large amount of reserves. And when the oil price is $100, if you want to separate the tar from the sand, the technology cost is about $70 per barrel. If the oil price is $100 per barrel and you start fracking, you will be making $30 per barrel cash profit. Okay, but if the oil price is 50, you have to close down your shop, because your investment is more than the returns. Okay, so there's economics angle, that makes it technology viable or unviable. So right now, all these projects of fracking are unviable and they have been closed because the oil price for the last few years is less than $70 per barrel. And then you have coal back methane. That means in the coal back you have methane. You extract it. Then there are gas hydrates. Gas hydrates means in the shallow sea bed, you have methane in the forms of crystals, because as you keep on going in the in the ocean, the water pressure builds up. Now in the ocean, what happens that there is a lot of marine life. So when this marine life is over, so all these bio remains get converted into methane, and under pressure they don't really come out of the ocean, they really get crystallized in the bottom, and if you can take them out, that will be energy source. So coal bed methane is also being explored. Not only it is because of the biological remains, it's also because the ocean absorbs a lot of CO2. Finally, through biological process, it gets converted to methane and it is stored. CO2, the largest thing for CO2 is ocean. Okay. Then, new oil production techniques have to be developed. More oil fields have to be explored if we have to meet our energy demand. We have to develop coal technology. So, coal is available in the world easily for 150-200 years. In India, we have enough coal for 200 years. So if we can develop coal for meeting our energy demand, clean coal technologies, now that will also be very important for future. CO2 sequestration. CO2 sequestration means if you are using fossil fuels, you are putting the CO2 into the atmosphere. If you can somehow capture it and store it in the underground mines, or somehow you can pack it inside the crust of the earth, naturally created cavities, then you are actually saving the atmosphere from that CO2, and you are saving the earth from getting heated up because of the greenhouse effect. So CO2 sequestration is also being looked at very carefully. A lot of work is going on CO2 sequestration. Then nuclear energy. Nuclear energy really does not have any emissions. The only problem it has is in case of accidents and also waste fuel disposal. These are the two main challenges. But otherwise it's very clean. I think this is also one route which the world can take. If If we come to the transport fuels, so this is the overall general scenario. Now I'll focus more on the transport fuels. So if you look at the primary transport fuels, they are primarily liquid fuels. Which are the fuels? Petrol and diesel, and maybe CNG to some extent. CNG is the only gaseous fuel. They are primarily made from crude oils and refineries. Okay. And why liquid fuels? Because they are the most dense liquids available in the world in terms of energy. You will not have any fuel, any other substance which will pack 36 megajoules of energy in 1 liter or 1 kilogram. Can you tell me? I mean, the only thing which has more energy than fuels is nuclear fuel. Other than that, there is nothing which contains more amount of energy. Okay? So that's why the liquid fuels in future are also going to be liquid fuels. Fuels in future are going to be liquid fuels. 70% of the liquid fuels are used for transport. 70% of that is used in cars. 30% is used in bus, trucks, and locomotives, and also in ships. Retail fuels is 95% fossil alkanes, and about 5% is from biological sources such as alcohols and biodiesels. These are the other fuels which constitute less than 5% in the world. Okay. So by 2020, the demand for this 5% bio-derived fuels will be $500 billion. So this fraction has actually, it is expected to increase. And I think this is one of the ways in which we can meet the growing transport demands. These are high density fuels. If you look at the energy density, gasoline is about 32 megajoules per liter. Diesel is about 36 megajoules per liter. They are easy to transport, store and handle. You don't need pressurized cylinders. There is no possibility of leakage unless the tank is leaking. Okay. It has extensive existing distribution network. So in next foreseeable future, the fuels are going to be liquid fuels. Now if you look at the growth projections of motorization, you know how the motorization will happen in the world and how the energy demand will be. So from 2000 to 2050, different countries are shown here. This is America. This is Europe. Do you see more change here? I mean, they already have more than one car per person. What change is going on? Right? So where is it growing? India, Asia, and China. Right. Okay. So number of cars are going to increase. Our paying capacity is going to increase. That means the demand for transport fuel is going to increase manifold. The government is supposed to supply, make a provision for supply of that. So this is going to be quite a big challenge for India. If you look at the fuel, there is no single solution for future fuels. This just shows the technology for cars. What kind of technology cars will be sold? Again, 30 years projection. You know now fuel cell cars are coming. Fuel cell cars will be very, very small towards like 2030 because their cost is still extremely high. Most of the cars will be gasoline cars. And then diesel cars are roughly 15-20%, and this will also lead to the same number. CNG, very small, 2-3% cars will be CNG, LPG cars, very, very small. What will happen is, although now is that new technology cars will come into the picture. And what is the new technology car? You will have a hybrid between diesel and HCCI. So it will be more switching between compression ignition and HCCI. Okay, so these cars will capture some market. Diesel hybrid electric vehicle. Diesel hybrid, diesel and motor. Diesel engine on board along with a motor. So there will be some market for that. Then gasoline hybrid electric vehicle, so a small gasoline engine and a motor. So I think the Toyota Camry and Prius, all these are gasoline hybrid. And there will be some small market for gasoline HCCI. So the India will switch between spark ignition and HCCI. So these are the new technologies that will come. Different fuels will come in. And there will be some room for flexible fuel vehicles. So flexible fuel vehicles means that you can switch between, say, alcohol. Whenever alcohol is available, you can fuel it with alcohol. Whenever alcohol is not available, you can switch to gasoline. It's basically any combination. Okay. So that's called flex fuel. So there will be some niche market for that. Now, whenever you are going for any new alternative fuel, you have to keep in mind four very, very extremely important factors. One is that what is the modification in the engine, existing engine hardware. Suppose I am saying that I have a wonderful fuel which is very cheap, and it will be nice if you can convert your car to run on this fuel, but it will require only an expenditure of 4 lakh rupees to make your car compatible with my fuel. And of course the price of my fuel will be half. Would you do that? Answer is you will not do that, because that will require almost your entire engine to be changed. If the extent of modification that is required in the engine for adapting to a new fuel is very high, then this acts as a deterrent. Okay. So first factor is that the extent of engine hardware modification required in the engine should be low. The second is investment cost required for developing infrastructure. Suppose you want to produce a fuel and it requires huge amount of investment in making the plant, processing plant to make that. Okay, so that will become a big challenge for the government to set up such a plant by investing huge amount of money. So one of the other attribute that is expected is that the plant to produce that fuel should not be extremely capital intensive. The third is environmental compatibility to the conventional fuels. So if your fuel is good, everything is alright, first two factors are met, but the only thing is that from the engine tailpipe you are emitting a lot of benzene, toluene, xylene and all kinds of unburned hydrocarbons which are toxic. Would you go for it? Answer is no. I mean, the emission regulation agencies will just say, okay, everything is fine, but we will not allow this. So the new fuel should actually be more cleaner than conventional fuel. Only then it will be allowed to be operated. And the fourth and the very important factor is additional cost to the user. So it is not just that you are paying only for cost of the engine or vehicle or cost of the petrol. It is also important for you that the new fuel does not damage your engine. Suppose on a diesel, the engine is going to last 300,000 kilometers, and with your new fuel, it is going to last only 20,000 kilometers. Would you go for it? Answer is no. If the new fuel requires the engine to be serviced after every 500 kilometers compared to conventional fuel where you require to service only once in 5,000 kilometers, would you go for it? So that's also an option. So that means additional cost in terms of routine maintenance, in terms of engine wear and tear, and also lubricating oil change should be low. Only then it will be accepted. So four factors: extent of hardware modification should be low, infrastructure cost investment should be low, and then it should be environmentally compatible, and then additional cost to the user should be low. These are the four guiding principles. If these are met, only then a fuel will be seriously considered as an alternative fuel. And whatever fuels we have discussed, please keep this in mind and tell me if any of these factors is not met. If it is not met, that fuel will not succeed in the market.